Hi everyone! This is a continuation of my video about polar coordinates in shaders. If you haven't seen it yet, I definitely recommend watching it first. Everything will be then a bit clearer. The link should be included in the description. However, I will also mention the basics in this video. So let's make some spiral effects. The effect you saw at the beginning of the video was created using a logarithmic spiral. It is one of the shapes that often appears in nature or can be observed, for example, on the edges of the Mandelbrot set. The logarithmic spiral is characterized primarily by the fact that, unlike the Archimedean spiral, the distance between individual arcs increases with the increasing distance from the center. It is important to pay attention to this, so in our shader we enable easy modification of the basic parameters of the spiral to adapt it to specific requirements. Let me switch to Godot, and as usual I'll begin with creating the scene, the color rect and the material with a shader. Right click on the scene, create new scene, let's call it spiral and create. Now right click, add child node color rect, and we'll give it the proper dimensions, which we usually set to 600 by 400. And the material, as I said, a new shader material, click shader, let's create a new shader, call it spiral of the type canvas item, and we'll put it to the shaders folder and create, and click to open in the editor. Very well. So the shader is ready, I mean the very basic skeleton of the shader code. Let's create the usual foundation. Okay, so we don't need the vertex function, I'll get rid of it. Sorry, and the light function as well. Very well, so I usually start with setting up the resolution just to fix the aspect ratio. Let's do it here, vector 2 resolution is a vector 2, and we set it to the dimensions of our color rect, which is 600 by 400. Okay, and the spiral we want to create should have some color, so we don't work only in black and white. Let's define it here. Uniform vector 3, as the color has 3 components, red, green, blue. Let's call it spiral color and give it a hint source color, so the inspector at the right side would show us a nice color picker, and the default value would be, for example, 0.2, 0.6 and 0.3. This time it would be something greenish. Very well, we will need a function to calculate the spiral itself, so I'll call it draw spiral, spiral, and with parameters vector 2 uv for coordinates of the current pixel, and float rotation. Our effect will rotate to give us a feeling like we are running through an infinite tunnel, so this is why we introduce this parameter to control this rotation. But right now at the beginning we just simply return 0 just to make the function valid. And now the usual setting up of the fragment function. I will put the origin to the center. As you know, if we work with UV coordinates, they go from 0 to 1, and the point 0, 0 is at the top left corner, 1, 1 is at the bottom right, so the center is actually 0.5 and 0.5. If we want to have 0, 0 at the center, it's necessary to shift the origin this way. Okay, and now to fix the aspect ratio, because we are working with the rectangle, so we need to multiply the x coordinate, uvx, and multiply by the division of the resolution parts x and y. Okay. Now we want to call the spiral function, function draw spiral. What's wrong? Dot is missing, I'm sorry. Let's fix it. Draw spiral. No, sorry. Spiral, just because draw spiral is the function with the parameter uv, and the rotation, it won't rotate right now, we will add it later. Let's work with 0 for the time being. And finally, we will define the final color of this particular pixel, which is basically the result of the draw spiral function multiplied by our spiral color to colorize that spiral color. Here we go. And of course we need to assign the result to the internal variable color, which is vector 4, so it consists of the vector 3 color and 1.0 as the alpha value. Okay, nothing is here because we are returning 0, and 0 is the black color. Anyway, the framework is ready and we can proceed to implement the spiral. Instead of the abstract coefficients a and k, as we could have seen in this Wikipedia page, is here in these formulas, I will simplify that and use only one parameter called frequency. Let's do it. So let's add another uniform parameter, uniform float frequency, and I will give it a hint range, so it can be there would be an easier way to set it in the inspector. Range would be from 1 to 0 with a step 0.1, and the default value let's set to 8. Alright, so since the spiral is most easily described using a function in polar coordinates, we will also work in polar coordinates. First, we'll convert the UV coordinates into the polar form, then we'll calculate the coordinates of the spiral using logarithms and exponentials. We must not forget the period of twice pi, so we will multiply or divide the calculations by tau, which is double of pi, as needed. Let's do it here. So first, float. Let's call this polar coordinates UV radius, because as we know, the polar coordinates are defined by an angle and a radius from the origin. So that's what we will do here. Radius is defined by the length of UV coordinates, the original Cartesian, and the angle I will call UI phi, and this is the result of the tan function of UV y and UV x. Okay, and we must not forget to add the rotation, which we don't use yet, but we will, and it's a good idea to implement it in our algorithm from the very start. Okay, so we now have the UV coordinates of the current pixel transported to polar coordinates, and it's time to apply the formulas from the Wikipedia page to implement the spiral calculation. I will start with calculating the angle and call it spiral phi, and it would be logarithm of the UV radius multiplied by the frequency, And from this we need to subtract the angle of the original coordinates uv phi. And since the spiral is a periodic function, we need to implement the period here and divide the result by tau. Okay, this is the first part, and the second part would be spiral radius. That would be simply the exponential, the inverse function to the logarithm, and the correct formula is this one. This time I will multiply by tau and use a floor, which is simply the integer part of the float value and the integer part which is less than equal to the argument, which is spiral phi. Okay, so it will ensure that tau is always multiplied by an integer and the period is preserved. And we need this time add the uv phi value and divide the result by the frequency. It is simply a modification of the formula we could have seen here in the Wikipedia page, and after a while we will see that it really creates a logarithmic spiral. All right, and now we don't need to return 0 anymore. We will return the spiral radius. Sorry, too many semicolons. Okay, and here we go. As we can see, some spiral is already being displayed. Let's try to rotate it. I will add a uniform parameter called speed multiplied by time and pass it to the function as rotation. Let's do it. So we will again have a uniform float, so I will simply copy and paste this line, rename it to speed, and the range can be, for instance, from 1 to 20. 0.5 step is correct, and we can keep the default speed at 8. No problem. And here in fragment function, where we call draw spiral, we will replace the 0 rotation by time, internal variable, multiplied by speed. Let's wait for it. Okay, it's rotating, and it already gives some impression of flying through a tunnel. Maybe we should lighten the final effect a bit, so I will add another uniform parameter called brightness, which is the usual trick I used in previous videos as well. Let's do it. Yes, brightness, and it would go from 1 to 10, for instance, and start at 5. So 5, so we can actually see something. Let's multiply the final color by this brightness. Color multiplied by brightness, and we can see that the default value is set to 8. No, it should be 5, and it is actually brighter. Very nice. That's not bad, but we still have room for improvement. What happens if, for example, we will use sail function instead of floor? Here it is, yeah. Sail is basically another transformation from float to integer, but this time we're looking for a greater value than the argument. We can see that it is a little bit different, but still pretty usable. Both variants have their merits, but the best would be to somehow combine them. We can try using the mix function, which performs linear interpolation. However, we will need a parameter to control the ratio between the two values. Let me add another uniform parameter called balance. And again, it would be a float, so copy paste balance, and it would go from 0 to 1 because we want to use it as a weight between two arguments of the mix function, and so the step should be a bit smaller. Let's try 0.01, and we will start at 0.5. Okay, and I will rename this variable to sail radius. Then we will create the original floor one, copy paste floor and the floor function. All right, and we would return a mix linear interpolation between spiral sail radius, spiral floor radius, and use the balance. Okay, not much has changed, right? It might be better to try the difference between the original radius, this one, and the UV coordinate and the spiral value. Since the difference can sometimes be negative, I will use absolute value. So I will copy that and do this. Absolute value of UV radius minus spiral sail radius, and likewise here, absolute value of UV radius minus spiral floor radius. Let's wait for it. Okay, this looks much more interesting, especially when we try changing the value of the balance. Let's do it. Okay, so it should be half, and now I will just drag it, and we can see some very interesting effects right here. All right, let's keep it at half. So what if we use some other option? For example, instead of using the mixed linear interpolation, we can try a maximum value of these two parameters. Let me try that. So instead of mix, I would use max, and maximum doesn't have any balance. Let's get rid of it. Very interesting. Now we can see some layers or gradients in the pattern of the spiral. What if we combine both functions using another linear interpolation? Usually, when I'm unsure how to proceed in creating an effect, I'll try a similar approach, like combining these mix and max values, and it often yields interesting results. So I will prepare that by copying this. It will be a long line, and I usually split it to multiple lines, but this time let me just keep it as it is. So it would be mix of this one first, max, and another max and balance as the parameter. And now I will change, because now it doesn't make any change, I will modify this, and it would be mix of these two values and another balance. Let's wait. Okay, maybe it's not too different from the previous one, but I think that if we play with the parameters, it can look, well, it can look interesting. Okay, and finally, we can enhance our effect by composing multiple iterations with modified parameters to give it a bit of a pseudo-chaotic character. First of all, I will create one more uniform parameter called octaves, which simply defines the number of iterations we will use to compose the final effect. Let's make it from 1 to 10, and the step would be 1. We don't want any fractional iterations, of course, and start at start at 4. All right, This is the uniform parameter, and now we need to use it. So instead of calling this, we will create a cycle. Float spiral would start at 0. I will just cut this and make it 0. And now cycle 4, float I starts at 0, I less than the number of octaves, and I increased by 1. We will have this cycle, and spiral would be increased by outdraw spiral. But of course we don't want to add the same value over and over. This is what would happen. The colors are adding up and resulting in very bright colors. So we need to create some modification. For example, multiply the speed by, let's try 0.5 plus sine of the I parameter. Okay, something is changed. It's still too bright. That's because we add too many colors, so the final color should be then divided by the number of octaves. So spiral is divided by octaves to normalize that. Okay, much better. What happens if I play with the parameters a little bit? For instance, I can increase the number of octaves. Alright, now it's a little bit more chaotic if I change the balance. Maybe too many octaves. How about I decrease the number of them? Just 2 and change the frequency. This is interesting, isn't it? And make it a bit faster and maybe brighter or darker, and change the balance again, increase octaves. We can do any kind of periodic effects with that. Cool. And that would be all, I guess. Of course, if you're not too happy with the last step involving octaves, you can always go back to the original standalone spiral and create new effects using frequency and balance. Anyway, I hope this video was at least somewhat instructive, and if it brought something new to you, I'm very pleased with that. So take care and see you in the next video.